Good afternoon, everyone, and welcome to today's webinar on digital solutions for railways. This event is brought to you by the EU and Shift to Rail funded project Intertrack 3. My name is Mats Tibon, Communication and Funding Consultant at Spinverse, supporting the coordinators Trafikverket, the Swedish Transport Administration. Reaching out with our results is very important for us at Intertrack 3. And this webinar and the previous ones are part of our outreach and exploitation activities. In this webinar, we will present 3 of our key exploitable results and also get the perspectives from the infrastructure managers on these results. The results are a digital twin solution for crossing panels, track design and maintenance guidelines to reduce curve squeal, and a new methodology to predict the long-term performance of the transition zones. You as audience will not be able to use camera or microphone in this webinar. However, the chat works and so does the reaction button. So please go ahead and ask questions and discuss in the chat. After each session, we will try to answer some of the questions depending on the time. Our presenters may also be able to answer in the chat or after the webinar has ended. Joining me today is Intertrack 3's project coordinator Pernilla Edlund from the Swedish Transport Administration. Pernilla, would you like to share a few words?
Yes, I would. Thank you very much, Mats. My name is Pernilla Edlund and I am the coordinator of Intertrack 3, meaning that I'm trying to pull this thing together for the past 3 years now, and we are closing by the end of this year. So we can show the next slide, please. And the next after that. Thank you. Intertrack 3, very briefly, consists of 26 partners spread all over Europe, and we have a broad participation from the important areas that the railway industry touches, meaning the universities who take forward the research, and also the infrastructure managers who are the ones who eventually need to have this or are the need requirements owners for the things that we take forward, because the infrastructure manager will want to implement this into their facilities. And also a fair share of product companies who take forward new products or methods to enhance the railway in Europe. Take the next. What we do is that we build on previous projects, 3 of them or more, depending on how you count. And this is the final project, and our goal, our aim, our purpose is to build on work that have been done previously that were more of a drawing table product that we are now testing out into track at TRL levels 7. With for many of them, we have like 30 demonstrators of the TRL 7, meaning that we're testing it out in operational track. And this is just an illustration to show. And here are more, no, we can, and here are a few more of the demonstrators that we have. And we have, as I said, we have 30 of those at high TRL levels, which are very interesting to learn more about. And if you want to learn more about this, you can join our final event on November 30th. It's a hybrid event. It's a whole day event, but it's divided into blocks. And you will find the detailed program at intertrack3.com, where you can also see the blocks in themselves and also the specific topics and speakers. So you know that this is something that really interests me. Okay, I'll join between 11 and 12 or whatever. So very welcome to register and to participate in that event. Thank you very much.
Thank you, Pernilla. Now for the first session today is the digital twin solution for crossing panels. So I'd like to invite Björn Pålsson, Chalmers University of Technology, and Arne Nissen at the Swedish Transport Administration. Welcome.
Yeah, thank you very much.
Thank you. And I believe Arne will start. And we have been working with sensor technologies for the purpose of looking on how bad or how good a crossing panel is performing since 2017. And Pernilla mentioned Interrail, and we started this already with a project called Capacity for Rail. And since last year, we have also bought these sensors on a commercial contract. So we use the sensors to find which type of maintenance decision that we can make for the crossing panel. So we can divide these into at least 3 different maintenance action we want to guide. And it's manual grinding, it's surface welding, and it's tamping or stabilization of the crossing panel. By using the signal, we do quite simple analysis. And the simple analysis is dividing it into either a good condition, green, or a warning condition, which is the yellow one, or the critical or bad condition, which is the red one. And you see there is a difference between the 2 graphs where the acceleration is shown with a calculated value, which we call standard deviation of the signal. And it's very simple and does not provide us with information when to do what. It just guides us that we have a problem. So if you take the next picture, please. When we have studied this during the years, we know that different things affects. Of course, the train type and the axle weight, the speed, and the number of trains makes the degradation go faster. If you have few trains, it takes longer time. But then we also have the effect of track geometry, the wheel condition, and the crossing profile. And what I show with the picture with the profiles is that we need to know when the contact is between the wheel and the rail on the crossing or on the wing rail, which is the red dot to the right. The accelerometer is the yellow square up in the picture where you see the crossing. It's placed on a sleeper, and therefore you can't see the reaction on the rail, but you see indirectly what's happening. And we can also plot things like the speed and the acceleration, and you see that there is a correlation between these 2. That's so far I've come as an infrastructure manager, and then we go further to the research.
Yeah, thank you very much, Arne. So yeah, at Chalmers University of Technology, then we have been performing independent research on this instrumentation concept. So we are using raw data from commercial sensors, but we do our own analysis using a digital twin concept. So we're working with something we call model-based condition monitoring then. So we use a physics-based model that is combined with measurement data continuously to create a digital twin for these condition monitoring purposes. And this is then work that has been performed by Marko Milosevic in his PhD project, and with supervision then both from Chalmers and from Trafikverket and Arne. And you see illustrated here the simulation model and the actual crossing panel in track, and they are then connected via the same sensor, so to speak. And that's a link between the virtual world and the physical world. And then in addition, in order to validate our method development, we have also been out to laser scan crossing geometries in order to understand what excitation is actually there in track. So though, go into a bit more detail, this is the research question that we have been working with. And it's then whether we can identify the crossing geometry irregularity, impact loads, and ballast properties from measured sleeper accelerations. So if we can go from an instrumented crossing panel to acceleration signal to these quantities. And The crossing geometry irregularity then, to start with, is the difference between the wheel and the rail vertical displacement. That's the rail as the wheel rolls over the crossing transition. So it's thus a measure of the irregularity or the dip that the wheel sees as it rolls over the crossing. And then the vertical wheel rail contact force and the ballast stiffness. So can we identify those from the measured acceleration signal? And our answer is that we can do it quite well. And this is then a study that has been built on accelerations and laser scan crossing geometries from 6 crossing panels on the southern main line in Sweden. And this is just an example then of how the crossing geometry looks like when it has been 3D scanned. So to go into some more details of the identification scheme itself, it's built on 6 steps. So it starts then with the measurement of the sleeper accelerations as shown before. Then Marco has developed a method for frequency domain integration to integrate the accelerations twice to sleeper displacements. And he did so, or he chose this frequency domain integration because it showed to be much more robust than the typical impulse response filters. Once we know the sleeper displacement, we can calibrate the ballast stiffness in the multi-body simulation model. And we have then identified the ballast stiffness at the particular crossing panel. Using this calibrated model where we know the track properties, so we assume that the superstructure has fairly nominal properties, so we don't expect the pad stiffnesses or sleeper and crossing stiffnesses to change much over time. It's predominantly the ballast stiffness that has local variations. So with that assumption, we can perform an inverse load identification using a Green's function approach. So we essentially take the sensor response and compute the wheel rail contact forces from the structural response. Knowing the forces, we can estimate the wheel and rail displacement and also then their relative displacement. So this crossing geometry irregularity or dip as the wheel rolls over the crossing. And so we can estimate this crossing irregularity, though in a limited frequency span. We can't do it at very low frequencies because the sensor is sort of nearsighted as it can only capture the response when the wheel is close to the sensor. But we think we can estimate then these impact loads up to about 250 Hertz and the crossing irregularity in this frequency range. So here is just an example then of the ballast property identification for these 6 crossing panel. So Marco has calibrated the ballast properties under the crossing, and we can do this independently of the crossing geometry. So we are looking at the low pass filtered frequency and the quasi-static response, so to speak. So we don't need to know the actual status of the crossing geometry in order to do this. So the result is independent of the quality of the crossing geometry. So we have a parameterization of the ballast stiffness underneath the crossing transition. And here are just 6 examples of identified ballast stiffnesses. And we see that for 5 of the crossing panels, we have an identified stiffness here. But for the 6th, the stiffness is essentially 0, which would then indicate avoided sleeper. And in this case, we had a sleeper displacement of around 6 millimeters. So it should definitely be voided. So that's the ballast stiffness identification. And then we go further to look at the force and crossing irregularity identification. So here I have a number of figures. So in the top row, we see results for identified responses from sleeper accelerations for a sample of axle passages. So it's 48 in this case, I think. And below, we have simulated responses from where we have implemented these scanned crossing geometries and the calibrated the ballast properties. And here we have used 20 different wheel profiles. So as we don't know what wheel profiles are passing the actual sensor, we compare on a sort of sample basis. And then responses we are looking at is the sleeper displacement then for a bogie passage, and it's the wheel rail contact force and the crossing dip or irregularity for the leading axle. And as we can see, the response is very good for the sleeper displacement. It's more variability naturally for the wheel ride contact force and for the crossing dip. But if we look at the overall trend as identified here with the dominant mode in a singular value decomposition, it's not so, the method is not so important that we have identified sort of the dominant trend in all these repeated signals. We can see that there's quite a good agreement. But if we look down on all 6 of the crossing panels, we think that there is overall good agreement, but there is more variability for some crossing panels than others. And the reason for that, we think, is that we have both uncertainty due to the wheel profile samples. We don't know exactly what wheel profiles are passing, and also the length of the scanned crossings. So we only have a few meters of scan, which means that we don't know the full excitation in the real crossing panel. So one would hope that the measurements would give the true answer, and partly it does, but without sort of getting even more field data and an even more detailed description of the actual measurement location, it's difficult to make a strict comparison. But yeah, what I just wanted to highlight 2 examples then of sort of a newer crossing geometry and a worse crossing geometry. So if we look at this crossing geometry, for example, Wetterid 1 or 2, and we can see in the green dashed framed figure here, we see this crossing irregularity dip or irregularity as a wheel rolls over the crossing. So this is the vertical trajectory of the wheel as it rolls over. And we can see that it doesn't have a very large amplitude. And we can also see then in our computed crossing condition indicators in terms of force and the RMS of this irregularity, that the values are lower here compared to the Wetterid 131, where we have higher forces and higher RMS values. And this is because we have this much greater amplitude in the dip for the wheels as they roll over the crossing. And this is then generated by just simulating 18 wheel profiles over the scanned crossing geometry. So we know what it should look like in terms of excitation. So yeah, that was it in terms of the digital twin and condition monitoring. And then I just wanted to give one slide on another thing we have been working with in IntoTrack 3, and which is the so-called whole system model. So it's a simulation scheme that accounts for the coupling between different damage mechanisms. So we can make a holistic assessment of a crossing panel design and see how design changes influence different damage modes. And we can also estimate the damage evolution of a crossing panel over time. But yeah, conclusions in terms of the condition monitoring. So we have demonstrated a model-based or a digital twin crossing panel condition monitoring scheme to identify the ballast and crossing geometry conditions. And we've shown that it's possible to identify with some accuracy the ballast stiffness, the wheel array contact forces, and this crossing irregularity dip in a bandpass filtered region. In terms of commercial interest, I know that there's implementation interest from commercial actors, especially for the displacement reconstruction algorithm. Some of the results here are yet to be published, so we have to see how much interest there is from that. And also in terms of practical implementation, we want to stress that these models for the different ballast properties, they can be pre-computed for a computational efficient implementation. So then it's more about picking the model with the right ballast properties in order to perform the load and irregularity identification. So it should be possible to do this online. Yeah, and I just wanted to say that we have this whole system modeling scheme as well. So, and publications, I will put them in the chat. So then I leave the word to Arne.
Yes, and I take a few minutes. When we work as a manager for the maintenance contracts, we have outsourced all the maintenance, it is a challenge to know when to do things and how we should be able to control what is done. And today, very much is done on inspection, or that we get fault in the tracheometry. And what I see is the visual inspection or the tracheometry does not give the information I want to do a good preventive maintenance. Then we can ask the question, is this the right method? Should we put out more sensors? And my view is we could do the same thing with trains that measure the acceleration, but it's even more difficult than what we have started. So by learning by one method, we can implement other methods to gain the same information. And what we actually want is to take decision much earlier, because today we decide what to do within a frame of 2 or 3 months. It should be possible to at least have the knowledge 6 months before. So I want to head for more proactive decisions. And that means the planning horizon for all the maintenance can increase. So the next picture, please. Going back to what we wanted intentionally was to divide the different maintenance action depending on what the signal says, not just green, yellow, and red. And I think Björn has shown that we can divide, we can be more precise what maintenance is needed. And I talk about failure modes as a general term. If we can identify the failure mode, we can also instruct what type of maintenance that's needed. And the last thing is, when we are done the maintenance, it should be possible for us to see that the condition is good again, that we can check this maintenance did the work we wanted. So that's all for me. Thank you.
Thank you very much, Björn and Arne. Actually, could we take one question that I see in the chat right now? What would be the value of sensor and data fusion from a large number of onboard sensors and accelerometers?
We have a project that's called MAI within Trafikverket that will take information from accelerometers on board trains. It has not been suited for turnouts, but we will use that information and see if we can succeed. But that's actually what I wanted to say. It's possible to measure this from the train. I think so.
Okay, so thank you very much. And if you have more questions for Björn and Arne, please ask them in the chat, and they will try to answer as well as possible there, or guide you further to read if they have information elsewhere. So next up is the track design and track maintenance guidelines to reduce curve squeal with Astrid Piringer from Chalmers University of Technology and Urs Schönholzer at the Swiss Infrastructure Manager SBB. Welcome.
Yeah, good afternoon. I hope you can hear me. My name is Astrid Piringer, and I'm working at Applied Acoustics at Chalmers University of Technology in Sweden. And I would like to present the work that we did about curve squeal in Intertrack 3. And the long-term goal of this work is to provide guidelines for track design and track maintenance to reduce curve squeal. See whether I can move on to the next slide here. Yeah. Okay, I would like to start with a short introduction to curve squeal. It's a highly disturbing sound that occurs when rail vehicles negotiate tight curves. And well, it's high noise levels and tonal sound, which makes it very annoying for the residents that live close to a curve, but also for passengers in some situations. And the reason behind curve squeal is self-excited vibrations of the railway wheel that occur during imperfect curving. Normally, the wheel sets are constrained in a bogie, and during curving, they cannot take a completely radial position, which means that they can not only roll, but also have to slide laterally during curving. And this lateral sliding provides the energy input to self-excited vibrations that then result in squeal. And squeal is in many ways challenging. It is challenging to model because it's nonlinear and transient and depends on many different parameters. It's also challenging to measure because it appears rather chaotic than deterministic, and also depends on environmental variables such as temperature and humidity that change from day to day or even from hour to hour. And it is also challenging to mitigate because measures work in one situation but don't work in another situation. So there's a lot that we still don't know about curve squeal. So the agenda of my contribution is I will shortly present our model and how we improved it during Intertrack 3. Then I will talk about the influence of rail grinding on curve squeal, and this actually showed to have a significant influence. And at the end, I will present some first results about the influence of rail pad stiffness. So here you see our model in a nutshell. It's a time domain model called VERAN that includes the high frequency wheel-rail interaction. And recently we also have implemented, or my colleague Yannick Thijssen has implemented a module for noise radiation. So this tool covers both curve squeal, but also rolling noise and impact noise. And it includes a flexible wheel model, a waveguide finite element model of the rail that is either continuously or discretely supported, and a detailed contact model based on Kalka's variational method. And then we use a Green's function approach to solve these three models together, which leads to high computational efficiency. Then in Intertrack 3, we have extended this model to transient curving. So previously we only could consider quasi-static curving, but now we can consider that the contact position changes during curving, and also a varying creepage, which is the sliding velocity normalized by the rolling velocity, and other varying parameters such as the friction coefficient. And I just would like to show one result from such a simulation, which is a purely theoretical result, but it still gives some insight into the phenomenon of squeal. So here we varied the friction coefficient sinusoidally with the position along the curve. And in the lower plot, you see a spectrogram of the lateral contact force. So the spectrum for each position. And at all positions where you see these horizontal lines, we have squeal. So there we have a fundamental squeal frequency and higher overtones. And well, here in this example, we first get squeal when the friction coefficient reaches a threshold, which is about 0.3. And then it stops again when the friction coefficient increases further, and starts again when the friction coefficient falls. And then this pattern repeats. And that the squeal stops again, I found that very interesting. And when you, no, wrong direction. So when we have squeal, we have a stick slip oscillation in the contact where we are oscillating on the global friction curve between cross sliding and partial stick. And you need to be at the limit between cross sliding and partial stick to get squeal. But if we increase the friction coefficient further, then the global friction curve changes as well. and this limit moves to higher sliding velocities. And then the same oscillation is not in the range anymore where we can sustain squeal, and squeal stops. And you can also see in the spectrogram that the first time we get squeal, it's at a different frequency than the other times, and this is due to the initial conditions of the simulation, which shows that the history also plays a role for the selection of the squeal frequency. Then what we've also done in track 3, that we have combined our model for high frequency wheel-rail interaction with a model for low frequency vehicle track interaction, where we chose the commercial software Sympac. So we first used Sympac to calculate, well, the low frequency vehicle track interaction for a certain vehicle configuration, track geometry, or train speed. And this gives us the time series of the contact positions and creepages that we then use in VRAN to get the time series of the contact forces and wheel and rail displacements. And we could also calculate the contact pressure next to the track, but we haven't done this in this project. Okay, that was the model. And then I will move on to the influence of rail grinding. And there I would like to present some results from measurements, which are actually from outside into track 3, from a national project about curve squeal.
Astrid?
Yeah.
Sorry for interrupting, but there are a few people that have trouble with seeing what you share. I see what you share, so could you try and stop sharing and then start sharing again and see if they can see it then?
I will try that. So now I've shared again, and I go back into full screen. So I hope it's better now.
Yes, so let us know in the chat if you still have problems. Thank you.
Yeah. Okay. So the results I would like to show now, they are from onboard noise monitoring at Stockholm Metro. And this study has been carried out mainly by Olle Eriksson and Peter Torstensson from the Swedish National Road and Transport Research Institute, VTI. And there we had microphones close to the two wheels in a wheel set on several vehicles. And we have had a lot of data. We had data from almost 400,000 vehicle passages through 143 curves. And we've done a binary logistic regression analysis of the data to see the influence of different variables on curve squeal. And one of them was rail grinding. So in the plot below, you see the results of this for rail grinding. Each of the dots is one curve that has been ground during the period of observation. And we've compared the probability to squeal before, so in the months and weeks before grinding and after grinding. And well, you see different rail radius, different curve radius for the curves. And the coefficient that is seen on the y-axis tells us whether the squeal probability increases or not after rail grinding. And if this coefficient is bigger than 0, the probability increases. So for most of the curves, we had a higher squeal probability after rail grinding, and this was a significant result. Well, the data does not tell us why this happens. One thing that certainly happens is that the friction coefficient changes during grinding. But I believe this is an effect that does not stay for a long time. So I don't think this is the reason for the differences. Other possible reasons are the restoration of the rail profile. So ideally, it goes back to a nominal profile during grinding. And this influences where we get the contact on the wheel and the rail, which we know influences curve squeal. And another reason could be the removal of surface defects and irregularities, such as corrugation, as you see in the picture to the right. And we would have liked to replicate these results by simulations. But for that, we would have needed a lot of measured rail profiles from these curves before and after grinding, which we didn't have. But what we did instead is that we know that different rail profiles will influence where we get the contact on the wheel and rail. So we vary the lateral contact position manually in the simulations. So for all these blue lines here, which are combinations of contact positions on wheel and rail, we carried out a simulation to see whether we get squeal. And here you see the results, which are in the same order as the blue lines are on the wheel. And the result is represented as one single value, which is the level of the lateral contact force that we get. And here a red color corresponds to clear squeal and white is no squeal. So here is one result where we get clear squeal, and then we get an oscillation in the lateral contact force, which is a stick-slip oscillation, as you see in the zoom below the plot. So there you have the lateral contact force and the traction bound, which is the normal contact force times the friction coefficient. So where the two curves agree, it's slip, and where they don't agree, we have partial stick in the contact. And when we don't get squeal, well, it looks like this, just the lateral contact force is just a constant. So we have a certain range of contact positions where we get squeal, and outside this range, we don't get squeal. And I think this could be used to develop mitigation methods. So if we manage to move the contact position outside the squeal range, this would stop squeal. And one such measure could be an optimized rail profile. Then finally, the last part on rail pad stiffness. There we have done a rather small parameter study with a discretely supported rail that had a rail pad between the rail and the sleeper with different stiffnesses. So we had a very soft pad with 41 meganewton per meter stiffness, a medium pad at 400 meganewton per meter, and a stiff pad at 800 meganewton per meter. And then the blue curves show the contact force spectrum for the different pads. And the red broken curves are a reference curve that shows what we get if we block the squeal mechanism and only have excitation on the discretely supported rail. And here, when you compare the different cases and look at the main peak, you see that while the main peak for the soft pad is about 10 dB below the medium and stiff pad, which would mean a lower squeal amplitude. But as this parameter study was rather small, I would not generalize this result for now. So I think we need further investigations to state how rail pad stiffness influences squeal. So I come to my conclusions. We have a state-of-the-art tool that can readily be used to investigate realistic curving scenarios with regard to squeal occurrence and amplitudes. And with this tool, we have demonstrated there's a certain range of contact positions on the wheel tread that that leads to squeal. And with this knowledge, we could develop mitigation methods if we manage to move the contact positions outside this squeal range. And then I showed the influence of rail grinding on squeal, but we have to do further investigations to explain what is the reason behind. And we also need larger parameter studies to study the influence of track parameters such as rail pad stiffness. And this work will continue in a national project funded by Trafikverket with the aim to, in the long term, provide track design and maintenance recommendations for reduced squeal occurrence. So, yeah, thank you for listening. And I give the word to Urs.
Thank you very much, Astrid. I hope you can see my screen. And it is my pleasure to show you the view of an infrastructure manager on curve squeal. I start with a few application cases that we have, then the legal framework that we're in, and then I'll tell you how we are going to apply the results. So the first application case is the obvious one, when we have a train negotiating a curve and we have line-side residents that are influenced by that. There we have limit values that we need to reach by law. We cannot be louder than a certain level, and if we have squeal, then we get penalties, and that deduct from the budget of noise we can have. Of course, it is not a picture of an actual curve. We have a squeal problem in. I just wanted to show off some nice Swiss landscape. The second problem is a bit less obvious. We have a few stations that are constrained on how they are built. We see here a picture of the station of the Swiss capital in Bern. We have the station in a curve. So one part of the curve is here on the front. Then we have a straight section, and you can't see the exit in the back. So there's another curve here. And we have 12 or 13 tracks. And when we have squeal here, because it's covered with a roof, it has walls on both sides. So it's really like an echo chamber. And people complain very heavily about the squealing noise that we have here. Here we try to reduce this with some friction modifier systems to at least keep the problem at bay to some level. We have quite a strong regulatory framework when it comes to track design. We have track layout standards, European standards, and in the case of Switzerland, we even have some of the values for track design implemented in law, so they are really hard to change. Then often track design is based on a so-called design speed, and maybe the majority of the trains is substantially slower. This can then lead to non-ideal contact parameters between the wheel and the rail. Or also we see this very often when we have passenger lines in the vicinity of stations. So the calculated track geometry is always made with a train in mind that goes through that station without stopping. This might be 1 or 2 maintenance trains a year, and all the other trains are stopping. And this then creates a little bit of a, let's say, an offset that the intended use of the track by the trains is not what the actual use really is. And then for us as an infrastructure manager, also a very tough situation is that we don't know who's going to use our tracks. We have the TSIs, we have open access. So it might be that someone with a high-speed train wants to reach a village with very tight curves. It is technically possible. Whether it's a good idea is another question, but it has to be possible to reach all the stations, and then this can also lead to quite significant problems with squeal that we have with only certain fleets that are circulating on a line. And also as an infrastructure manager, it's not possible to mandate certain wheel-rail contact parameters from the railway undertakings at the moment. And that is why we are very keen on having guidelines that we can prove. So we need to know the exact correlation and then the dependencies of track design and maintenance. We can influence that, for example, by changing the cant or changing correctly gauge. And we have also to know the effects on the real whale geometry. Then vehicle design and maintenance has also an effect, and the friction modifiers. And we need to have a really good understanding. We need to quantify all these influences to match what I showed in the previous slide. We have a lot of regulation from the theoretical side, and that never takes into account noise. So we need to counterbalance that with a similar knowledge, what all these parameters and factors, what their influence is on the noise and especially squeal generation.
Urs?
Yes.
Can you finish in a few seconds? You think? I know this is your last slide because the next presenter needs to come in.
Yep, I'll do that. And how do we do that? We use the simulation results that we have seen here presented by Astrid, and we match that with the field tests to see if these results are really giving us the actual input that we are looking for. That was all. Thank you.
Oh, thank you very much. And regarding questions, please go ahead and keep on asking questions in the chat. And thank you very much, Urs and Astrid, for great presentations. Let's move on with the last session of today with Anna Ramos from the University of Porto and Matthias Asplund from the Swedish Transport Administration, who will present a new methodology to predict the long-term performance of transition zones. Welcome.
Thank you. Should I start then, or?
Yeah.
Okay, give me some seconds. I will make the presentation here. I will share the screen.
So be aware of it's 13:47. We are a little bit after in schedule, so if you could do it in 13 minutes, yeah.
We will do it as fast we can.
Yes.
All right, you hear me good? Yes. If I have had some problem with the connection, actually, if I'm disappear, you know that this is my connection. I have to log in 3 times, and the 3rd time will work. But anyhow, we will start to speak about the new methodology to predict the long-term performance of the transition zone. And me and Anna will go through this presentation, and I will start it and I will end it. I will frame the presentation from Anna. Let's see if I could find the next. Yes, here is the introduction. Sorry, I think this was the wrong head. This should be agenda instead of the background, because the background, I will take the background and speak about what is a transition zone, what's the problem with the stiffness change on track, and where do we have this kind of stiffness changes in track. Then will Anna take the presentation, the motivation, methodology, a little bit of the work she has been done in the Gransjö demonstrator and conclude that. And then I will end to mention a little bit about what do we think we could use this new methodology to, and how could we gain something in Trafikverket with this new knowledge. Transition zone, when we have this change in the stiffness of track and you have the same axle load, you will have the vertical deflections on track that will be different, and that will lead to different settlements in the longer term. And in this picture, I will show you a little bit of the idea to have these transition zones. If you, for instance, have a car, you have the free track and you have a bridge, you will have a point in between the free track and the bridge. There is some type of change in the stiffness, and this is more or less a step change, and step change are not good because they give a lot of dynamics in the vehicle, and this could be improved by having a transition zone instead, like this show with the smoother transition in between the stiffnesses. There is also a European standard that deals a little bit with this and mentioned that you should have this transition soon, that the settlement in the long term will be the minimum. And yeah, what's the problem? I think you already have a feeling of the problem, because when we have this fast change in stiffness, we will have the vertical deflection in the track, because you are passing a zone where you have different stiffness, and this will give dynamic motion to the vehicle, and the motions will be forces that need to be the track will take care of these forces, and these forces will lead in the long term to degradation, more degradation that you expected on track, which leads to maintenance actions. And if you go out and you need to have the track access to have these maintenance actions, and the maintenance actions usually consume the capacity from the operation. You can't have the operation in those times. Of course, you can have the maintenance also in the white times where you have no operation, but sometimes you need to have it on the time where you could have the operations. And this will cost in the loss of the capacity, and also you should avoid different stiffness changings to enhance the capacity and save the cost on track. There is also cost like a maintenance cost of track, the maintenance cost of vehicle, and the society cost like speed reduction, and also that the passengers feel bad comfort. And where do we find this? We find this in ballast and fixed track, in between open track and bridges, open track and switches, open track and tunnels, and for instance, even where you have these pipes. And how many bridges do we have in Sweden, and how many switches and pipes do we have? We have, if I account all these together, I think I get 60,000 different areas where we have change in the stiffness. Of course, these are not hot spots, all of this, but these are spots. Thank you, Anna.
Please, Anna, you need to unmute.
Sorry, I will share. I was telling that I will share my screen. So, okay. Moving on with the presentation. Are you seeing my screen? Yes?
Yes, we do.
Yes, okay. So I will talk a little about our motivation to do this work, some slides about the methodology, short-term and long-term performance, some aspects regarding the numerical modeling related with the demonstrator. This is work that is developed by University of Porto and Chalmers University, and also some conclusions considering this developed work. So regarding motivation, Matthias already presented. So we have here some in transition zones, the degradation process is more accelerated. So this is a problem in railway network, and there are serious problems related to differential settlements because of the difference of the stiffness of the structures. So in the analysis of the long-term performance evaluations, there are some difficulties or uncertainties in our analysis. So we should start with numerical models of ballasted and slab tracks. And probably it is important to do a numerical model validation in order to gain some confidence in our ballasted track models or slab track models in order to move on to transition zones, because transition zones present a very unpredictable behavior. So it is important to have confidence in our models in order to predict the long-term performance of the railway structures. So regarding the methodology that was developed in the University of Porto, we have a 3D numerical model of the vehicle track system, a 3D numerical model developed in ANSI. So this allows us to have an exact geometry of the track. And based on this, we are able to perform the dynamic analysis with the vehicle track interaction, considering contact elements between different layers. For example, for the ballast track, we can include contact elements between the ballast and the sleepers. And our main point is to obtain the stresses on the geomaterials of the track. Of course, that we are also able to analyze displacement, strain, stress, accelerations on the different layers or materials of our model. But the main point for the long-term performance is to obtain the stresses on the subgrade. So this is our short-term analysis, and based on the stresses of our dynamic analysis, we are able to predict the parameter formation of the substructure based on an empirical parameter formation model that I show here. This is an example of this type of models that are developed in laboratory, and they are dependent on the stress state of the geomaterials, initial stress state, and also the stresses that are induced in the geomaterials by the passage of the train. And from this parameter formation, we have a permanent settlement that can be again introduced in our 3D numerical model. And from this point, we have now a deformed track, which means that we are able to analyze a joint effect of the differential settlements and also the track degradation. So here is an example of the application of this methodology. This is a transition between an embankment and a tunnel, considering a slack track system. So we start with the stresses obtained in the 3D modeling in all nodes of the substructure. This is an example of the variation of the maximum stress of the subgrade along the track. With this, we are able to predict the permanent deformation, and we can have a variation similar to this. This is the maximum cumulative permanent displacement, which means it's the settlement accumulated along the track. And from this point, we now have a deformed geometry that can be inputted again in the 3D modeling in order to simulate the track degradation. So we start with a non-deformed track, and now we have a deformed track in our 3D modeling, which means that we will have higher stress, higher train-track interactions force, higher accelerations, and so on. So from our point of view, in the analysis of the long-term performance, the methodology should include dynamic analysis, vehicle-track interaction, a 3D complete models of the track. The simple 2D models are incapable because they cannot simulate the train load distribution. Of course, that we can tune our 2D models, and I will show the work developed by Chalmers. Of course, that the 2D models are faster than the 3D because of the time of the analysis, and the 2.5D models are not an option in this type of analysis. So from our point of view, the short but also the long-term performance are mandatory, should be analyzed together. And of course that if we need to calibrate or validate our model because the transition zones present a very unpredictable behavior, as I said previously. So regarding the demonstrator in Sweden, some of you know about this demonstrator. This is a transition between a ballasted track and the 3MB system. This system is a modular system, has 4 blocks on each side, as you can see here in this figure, and each block comprises 2 rail supports, and there is an elastomeric layer that allows to mitigate the vibration transmitted to the slab. So we start our analysis from the developing of our 3D model. So we have here our numerical model with a transition between a ballasted track and a 3MB slab track. Here is a detail of the developed model. And we simulate the performance of a transition zone between the 3MB system and the ballasted track, considering the passage of this train that I'm showing here, with a train speed of 60 kilometers per hour and an axle load close to 30 tons. So here we have the detail of the 3D model. The ballasted track, we have ballast to ballast and the remaining soil layers. And for the 3MB, we have the concrete slab, the sub-ballast also, and the remaining soil layers. So this work, University of Porto and Chalmers University are working together in order to improve both models, considering the measure experimental results. So from the Chalmers University, they are developing a nonlinear 2D track model based on an iterative approach to predict the long-term settlement in transitions. Sorry. The basic strategy is quite similar because at the end we are trying to simulate the track degradation, updating the track model, considering the settlements obtaining. So from this, the 2D track model, they start with the initial track model, then apply a gravity load, and from this point they simulate the dynamic vehicle track interaction. And this type of simulation is much faster than the 3D, so this is a main advantage. And for each slipper, from the slipper ballast contact force, which is one of the main inputs of this methodology, they are able to calculate the settlement increment and the accumulated settlement in order to update the track model and the threshold value in settlement model and start the analysis again.
Anna,
Yes.
I'm very sorry, but actually we are running out of time, but I will give you some more minutes. Can you,
Okay.
yeah, just so you know.
Yeah, I thought that I will have 10 minutes. So,
yes, I'm very sorry, but the
okay,
time
no
is,
problem. I will try to
go a few more minutes and try and wrap it up. Yeah.
Okay. So we have here the short-term analysis, the results for the ballasted track side, a comparison between 3D, 2D, and the measure results. So the 2D model is very close to the measure results for higher frequencies. For lower frequencies, the idea is to tune the 2D model based on the 3D because the covariance is low for lower frequencies. But you can see here that the results are quite good. We also have the slipper displacements, and there is a comparison here between 2D, 3D, and the measure results. The magnitude of the slipper displacements is in agreement for the three results, and also for the slipper ballast contact force, which is one of the main inputs of the Chalmers methodology. The 2D model and the 3D model, the results are practically overlaid, which give us confidence in our results 2D and 3D. From the slab track side, I also made a comparison between the experimental and numerical. So I can show you here that there are some agreement in terms of magnitude after the transition in the slab track side. So we have here a variation between 0.5 and 1 meter per square second. That is quite close to the magnitude of the acceleration measure on the demonstrator. From the long-term analysis, I select a longitudinal section and I predict the permanent deformation considering the contribution of the geomaterials using this empirical permanent deformation model that I showed you previously. And you can see here that the results, experimental results for slipper 11 and 5, these are experimental. The slipper 5 is close to the transition. And in the red curve, you have the numerical results for the accumulated settlement for slipper 5, and the magnitude is very close. The curves are not overlaid, but the magnitude is close, which means that the methodology can predict the long-term performance of the transition. So very fast, the conclusions show you that the developed methodology combines the 3D model with empirical settlement. The FEM model is capable of simulating train track interaction and use contact elements to simulate the voiding between different layers of the track, for example, slipper ballast for this case of the demonstrator. This methodology allows to include the joint effect of dynamic loading with track degradation, and this knowledge can be used to predict the long-term performance of railway tracks, especially in transition zones, because, as I said previously, they show unpredictable behavior. So based on these, the infrastructure railway managers are able to manage the maintenance operation based on the performed predictions or simulations using this methodology in particular. Thank you.
Thank you very much, Anna, and thank you, Matthias. I'm really sorry for rushing you on like that, but the time was up, and we hope that people have been managed to stay until now anyway. because it was really interesting presentations you had. So I would like to thank all the presenters for sharing your knowledge today and all the attendees for the participation. We hope you found this webinar informative and engaging. And make sure to follow Intertrack 3 and all organizations participating in this webinar on LinkedIn. And we would also like to invite you to our final event, November 30th in Stockholm and online, as you see what I'm presenting. You find the program on our webpage, intertrack3.com. So thank you very much, everyone, for participating, and bye-bye.